All right, welcome everybody to the SUSECon roadmap session on the SUSE Adaptive Telco infrastructure platform. My name is Tim Irnich. I'm the product manager for the SUSE Adaptive Telco infrastructure platform, and I have here with me Gary McKenzie. Gary, can you quickly introduce yourself?
Thank you, Tim. My name is Gary McKenzie. I'm Director in the Field Product Management organization at SUSE with responsibility for telecoms in the edge space.
All right, and with that, I think we'll dive right in, right? Gary, the first part is yours.
Thank you very much. So we're going to cover a few things today. First off, an overview of what ATIP is and the problem space we were solving for. Then we'll go a little bit into the high level on the components which make up ATIP, the architecture and the key features. And then Tim's going to take us through which features are currently coming up next and what's in the roadmap for the future. So if we dive on one slide, the first thing we want to talk about is the macro trends in the industry, which are informing why we've built ATIP, how we've built ATIP, and also how it meets them. So the first of these, and the big one, is this second wave of network function virtualization, or network transformation, if we want to call it that, where NFV is expanded into new use cases nearer the edge of the network. This is things like Open RAN, things like the fixed access network, where the first wave of NFV didn't really reach. In that space, Kubernetes and bare metal hardware is the platform of choice. I think we can say now that Kubernetes has won the infrastructure argument there. So it creates a new dynamic in the space, which has fundamentally changed things and has informed a lot of how we've built ATIP. The second trend is the general progress we've seen in the edge space more widely, but also the Kubernetes ecosystem generally around managing these small footprint Kubernetes clusters at very high scale. When we look at these new use cases, we're going to be moving into environments where we might have thousands, even tens of thousands of clusters to manage, and the ability to do that, but also keep their footprint small enough that they don't consume unnecessary resources is going to be key as well. Lastly, we've seen, as the first wave of NFV has progressed, we've seen operators become more comfortable with both open source and with the idea of diversifying their vendor ecosystem, acquiring more components from more vendors, and accepting the integration costs that implies for the benefits it gives. This has driven the need for the sort of independent open source cloud platforms that SUSE has specialized in and that ATIP represents. The key takeaway from this on the right of this slide is that ATIP is at its heart an open source telco cloud platform, which is focused on delivering the ability to manage at scale these small footprint Kubernetes clusters and also ensure these clusters are telco grade. In terms of what that looks like a little bit more, we can go on one slide. Thank you. So ATIP has three pillars, let's say, underpinning it. The first of these is, as I mentioned at the end there, this telco grade performance and small footprint. You can view this as the table stakes, the things we must have to have a credible platform in this space. So this is technical features, functionality that are required to run this new generation of telco workloads, but also the small footprint elements, the things like security and the like, which are must-have features in this space. And we're doing that using components which are purpose-built for the edge. And that's an important trend across ATIP as a whole, that we haven't taken a data center Kubernetes platform and squashed it into an edge envelope. We've actually thought about the requirements, thought about the needs of this platform, and then built from the components and the primitives to build this platform up from the bottom, rather than taking an existing platform and chopping bits off until it fits the space. The second pillar is operations at scale, and particularly simple operations at scale. So we think that GitOps is going to be a key part of this, and we've done a lot of work to build GitOps-based compliance and drift prevention mechanisms, so the idea of remediating towards a defined config. So that's a big part of how we operate this platform at scale, but we also acknowledge that you can't use GitOps for everything today, and it's maybe not desirable to. So having the easy-to-use GUI available when it's needed is also a core part of that, to ensure the user experience for our operations teams is what it needs to be. Lastly, the third pillar here is the proven integrations and certifications. We want to ensure that this platform works and works predictably on a wide range of third-party telco-grade hardware. It integrates cleanly with third-party SDN solutions, and there's a wide range of applications which work out of the box on the platform. If we skip on one, we can see a little bit of what the architecture looks like for this. Now, ATIP is comprised of a management stack and an edge stack. Each edge site is going to have at least one instance of the edge stack running there, and it consists of SLE Micro as an operating system running on top of either bare metal or a cloud environment. We try and treat all the substrates equally in terms of functionality as much as possible. And then, excuse me, on top of that, we have an edge-grade Kubernetes in the form of K3S or RKE2, along with our add-ons NuVector for zero trust container security or Longhorn for cloud-native storage. And then on top of that are the applications at the end of the day, those container or VM workloads. And it's important to call out the VM workloads here as well, as Tim will be talking about in the roadmap. We are bringing the ability to run virtual machines to the edge alongside containers where necessary as part of that roadmap. Then we have the central management stack, which is where we aim to manage the entire life cycle of these edge sites from. So we're bringing in, on top of Rancher Prime as the core platform, components to support the GitOps methodologies I talked about in the last slide, but also things like Cluster API and Metal Cubed for bare metal management into that platform, so they provide the lifecycle features for all those sites at the scales we're talking about for these use cases. From there, I'm going to go through some of these individual components in a little bit more detail to talk about the features that they individually bring. So, excuse me. The first of those is SLE Micro. SLE Micro is a container-optimized Linux. It is built on modern paradigms, modern technologies, as you'd expect. It is a minimal footprint operating system. It doesn't have more than is necessary to run containers in there. It's very much focused on this role. And because of that, it has a minimized attack surface. It has an immutable file system, which helps it be secure by default. And we do a lot of work to ensure it's meeting all these security profiles and requirements, which are so common in the industry. It has transactional or image-based update mechanisms, depending on which fits for a particular use case. So it's flexible, but supports both these mechanisms for updates. And key for the edge space, particularly as we push towards the far edge, it supports ARM and x86 equally. Beyond that, there are also the telco-grade features, which, again, I referred to previously in ATIP. These are the things which are table stakes for running these applications, and we must have things like the real-time kernel and precision time protocol for when we're talking about Open RAN applications, things like DPDK for fast data path. On top of the operating system, we have our edge-optimized Kubernetes offerings, and they take two forms. Firstly, and we feel the default for most people for ATIP use cases is going to be RKE2. So RKE2 is a downstream of K3S, but it's security hardened and certified. And part of this is because it was originally built and optimized for government and regulated industries like telecoms. It supports all the telco-grade CNIs you'd expect, things like Calico and Cilium, but also integration with third-party proprietary SDNs, and we'll talk about that a little bit more in the roadmap as well. Then we have K3S, which is the upstream of RKE2 and a CNCF project. It is the world's most adopted small footprint Kubernetes. It has a really small binary installer, less than 70 megabytes, so it's a good fit for the use cases where we have really tight requirements on the compute capacity. So things like universal CPE and such, we see a use for K3S, and that's why we bring both products to the table here. Lastly, from there, we go on to Rancher, which is our solution for delivering the management of multiple clusters at the sort of scale we need here. So Rancher is built on sort of a long and outstanding industry adoption. It's important to say that Rancher can manage any CNCF compliant cluster, and that's an important quality when we're talking about the move towards hybrid environments where we may be managing clusters in public cloud, or indeed some vendors may be bringing their own Kubernetes to the table in some environments. So the ability to manage multiple clusters from multiple vendors is a key piece, as well as our own stack here. It has, as we spoke previously about the operational piece, that user-friendly GUI. So we're looking to build a fantastic user experience here and make sure the features are exposed to users both through this, but also through that GitOps-driven methodology as well. And it has a large marketplace with proven integrations, whether that's storage or LMA stacks or the like. There is an extensive selection of pre-existing integrations in the marketplace. Now, we've extended Rancher for SUSE Edge generally, and also for ATIP specifically, with a number of components. These include Cluster API, which gives us that API-driven cluster lifecycle management. It's a really powerful stack, which gives us the ability to use its modules and to leverage what it brings to the table in terms of allowing different infrastructure providers and, in due course, potentially different Kubernetes providers if necessary for customers. We build that alongside and to an extent on top of our bare metal management capability, which the underlying project we use for that is Metal Cubed, which gives us the ability to stand up bare metal nodes from scratch in a secure fashion. So we're not relying on unencrypted protocols here. We're not relying on PXE. We can use virtual media boot to ensure booting these machines in a secure manner. So that gives us a modern bare metal provisioning capability, which integrates nicely with Cluster API through that infrastructure provider. And finally, the other big integration we have for the Edge and for ATIP is our cloud native operating system management with our Elemental tooling. Again, another open source project that we've brought to the space. Elemental allows us to treat the operating system like a Kubernetes artifact, so we can start to move the management of the operating system into Rancher and into Kubernetes using the same sort of primitives that we do for the applications themselves, and it makes it a much more unified management experience for the entire stack. Now, I've run through some of the components and what the architecture looks like here. I'm going to hand over to Tim at this point to talk about what this looks like when we deploy it, what the process is like, and how we do this at scale. Over to you, Tim.
Yeah, thank you, Gary. So as Gary already touched upon briefly, the one very important quality of an edge stack is not necessarily how well it supports the workloads, but also how easy it is to manage many instances of the underlying infrastructure and the workloads. Because what managing edge infrastructure at scale really means is the typical paradigm or the typical pattern is that there is a small number of infrastructure footprints, or maybe only one, which then get deployed many, many times. So what we typically see, and that is not actually typical for the telco industry, that's valid for edge in general, is that there are usually a large number of clusters based on one or a few blueprints or templates. So the management stack has to provide an elegant way for customers to manage infrastructure according to that pattern. And we believe that GitOps provides exactly that. So the typical workflow will be you check your cluster template expressed through, for example, a YAML file. There are theoretically also other options in terms of which language you want to use to express your definition. But Kubernetes YAML is, I guess, what everybody will understand works in this case. You will check that into a Git repository, and that definition includes everything. It defines how your operating system should be composed and configured. It defines how your cluster should be set up on top of the operating system. It defines how many nodes your cluster has, what the allocation of worker and control plane and data plane roles to those machines is going to be. It defines how your workload should be deployed. It defines your policies, your role-based access control, everything. You will, as soon as you have that stored in a Git repository, you can instruct your GitOps engine to sync that cluster definition to our Rancher Prime-based management server. And what that will create is it will instruct the management server to turn that definition of wanted state into actual infrastructure state. So all the reconcilers, all the operators on the Rancher management cluster will pick up that definition and then will bootstrap your infrastructure. In the case of doing this through Cluster API, the way this works is that the first thing that happens is your infrastructure provider provides you the underlying infrastructure, depending on what infrastructure you're using. If you're using Metal Cube as a bare metal infrastructure provider, what that means is picking machines from the inventory of available bare metal and deploying the operating system according to the specification created in the first step, and then deploying the downstream Kubernetes clusters and all the additional tooling and the workload on top. So that is now, of course, just an example of a day zero workflow. There are, of course, also the longer-term lifecycle management workflows, which we don't want to go into too much detail here. But the important takeaway here is that it all gets controlled by those templates that you check into your Git repository, and that this Git repository is the single source of truth. So which basically means that if you want to change something in your infrastructure, the canonical way of doing that is to actually make a commit to your Git repository that contains the desired change. And from there, the tool chain of automations that we're providing to you will pick up that change and roll it out into the infrastructure. Of course, including the possibility to, for example, do canary rollouts, phased rollouts, and of course, you also can control what gets rolled out to which section of your infrastructure. It's not an one fits all kind of thing. You can, for example, regionalize your fleet of downstream clusters and say, I want this change to be rolled out into this region. I want that change to be rolled out into that region, and so on. And with that, we can come to the roadmap itself. So this is, of course, a busy slide, and I will take you through it step by step. So let me tell you first what the columns in the table mean. So the now column basically describes what are the most important elements that we have available today, which were recently released or which are important aspects of the currently available functional scope. Then the next column basically roughly spans a time horizon of 6 months, because we're planning our next big functionality drop for the fall this year, somewhere in towards the end of Q3 or beginning of Q4. The exact time hasn't been determined yet, but this is roughly a 6 months time horizon in terms of new functionality. And then everything that is beyond this 6 months time horizon is in the last column, which we've denoted future here. Talking about the 5 different rows in the table, we've separated, let's say we have identified 5 different distinct areas of developing additional functionality. The first one is provisioning and lifecycle management. We've already talked about that extensively. So everything that has to do with automatically rolling out your infrastructure to edge locations without requiring more than the minimum of technical personnel on site and more than the minimum of manual physical intervention with the system is in this row. The next one is the GitOps engine, which is essentially an enabler for the zero-touch provisioning, but we are denoting it as a separate column because it enables certain operational paradigms, and that's why it makes sense to call it out separately. The telco profiles and everything that has to do with enabling the edge stack to effectively support telco applications is in the third column. This is what Gary referred to as the table stakes that we have to provide to really be able to claim that we have a telco-grade platform. And then we have hardware enablement and everything that has to do with third-party, either ISV or IHV certifications, so either independent software vendor certifications or independent hardware vendor certifications, is in the fourth column. And then we have observability as, of course, one very important aspect of managing edge infrastructure, because if you don't have qualified people on site and if you have to manage a very, very large number of clusters, having powerful ways of not wasting your time with looking at unimportant data, but being able to identify and focus your energy on the important data is key in this area. So let's go through these rows one by one, and I'll take you through where we are today, where we're going within the next 6 months, and what is beyond that. So when it comes to provisioning and lifecycle management, what we currently have is a tech preview of a new RK2 bootstrap provider, which enables the use of RK2 as a Kubernetes distribution in the context of Cluster API. So the bootstrap provider is a specific provider type that the Cluster API architecture foresees as the element that turns an infrastructure node into a node in a Kubernetes cluster. We also have a tech preview of our Metal Cube infrastructure provider, which enables us to turn physical machines that we manage ourselves or that our customer manages themselves into Kubernetes nodes and provide them to the bootstrap provider for provisioning. So those two components have been either newly created or productified from upstream, and they are in tech preview right now. Within the scope of the next 6 months, we will make those two components generally available in the sense of that they will be on the official price list and that every customer will be able to purchase them from us or purchase support for them from us. And then this will be accompanied by a tech preview of integrating Cluster API into Rancher and exposing the API as an actual provisioning mechanism. The further roadmap beyond that in this area is that there will also be a graphical user interface within Rancher in the form of a GUI extension for bare metal management. That this Rancher integration of Cluster API I just talked about will become generally available. And then in order to enable the specific use case of air-gapped edge clusters, we will create functionality to support Rancher-less bootstrap of air-gapped edge clusters. So right now, the bootstrap of edge clusters requires connectivity to the central management cluster, and that is obviously not always the case in air-gapped scenarios. So we are enabling a scenario where you can bootstrap your edge cluster without having connectivity to a central Rancher agent. And then at a later point in time, if your use case allows it, you can still connect to it and have, in some cases, limited functionality because certain aspects of the connectivity prohibit certain functionality of Rancher, but the other elements should, of course, then still be available if the use case permits it. Moving on to the GitOps column, to the second row of the table. What we are supporting right now is programmatic management of and workload cluster provisioning through third-party GitOps tools, for example, Flux CD or Argo CD. And the downstream cluster tools and workload management can happen through our own GitOps engine, which is called Fleet, which is the technical foundation for a module within Rancher, which is called Rancher Continuous Delivery. We are right now enhancing Fleet so that it can be used for GitOps-based workload cluster provisioning as well, or downstream cluster provisioning. And at the same time, we're adding drift reconciliation to Fleet because that is obviously a very important feature to realize the operational paradigm I talked about on the previous slide. At a later point in time, we will also add a powerful templating mechanism and provide more fine granular deployment controls within Fleet. And what that means is right now, the ability to control the rollout through Fleet is limited to being able to determine the sequence in which multiple Git repositories are synced to a target cluster managed by Fleet. And in the future, this will also be possible for resources that sit within the same repository. And there will be additional controls in the sense of, for example, waiting until a Kubernetes deployment has reached the right stage of its deployment cycle, and then deploying the next bunch of resources, which may depend on that functionality being already available. In the area of telco profiles and related tooling, we already support Cilium and Calico as two widely adopted CNI options within Kubernetes, and we also have Multus and a number of additional tools, such as, for example, Whereabouts, for scenarios where multiple interfaces are required in a Kubernetes pod, which is canonically the case in telco use cases. We also have Helm charts for node feature discovery, and we are supporting topology-aware scheduling within Kubernetes. We have a real-time kernel option within the SLE micro operating system that's part of our stack. And of course, that kernel supports CPU pinning, ISOL CPUs, and also huge pages We have recently made the RKE2 SRIV operator generally available, which includes auxiliary components like node feature discovery and the Intel device plugin. So we are relatively feature complete when it comes to the table stake functionality within a Kubernetes context to support telco applications. The next step after this is that we will start providing a number of boilerplate profiles which provide typical configuration settings for all those layers of the stack. Having the functionality available as such is, of course, only one part of the equation. You also have to configure it accordingly so that your application really works well. We are going to extract commonality across the different use cases we see across customers, and we are going to provide those profiles as a starting point. They will usually require a mild degree of customization for particular customer use cases, but we believe we can get our customers 80% of the way so that integration projects can be sped up significantly. At the same time, we will also provide additional tooling and functionality to control network customization, configuration of network interfaces in the operating system, exposure of SRIV devices into Kubernetes pods, and all that. We are at the same time also working at a integration of KubeVirt as the underlying mechanism for virtual machine support, and we will also provide an integrated GUI within the context of Rancher for that part of the functionality. We will provide Metal LB as a bare metal load balancer option because obviously many bare metal use cases will require that. And with the move to the new version of SLI Micro 5.5, which is scheduled for October, we'll also provide a recent DPDK version in the form of 22.11 long-term support. Further down the road, beyond the 6 months time horizon, we will make the before-mentioned network customization generally available. We are planning an evolution of telco profiles into a generic template library for cluster profiles, which will then also have a graphical user interface component, and we will make that that part of the functionality generally available at a later stage. And our long-term trajectory when it comes to DPDK support is not only to support one long-term support version, but all versions of DPDK that are under long-term support in the upstream community. As far as hardware enablement goes, we are already certified on Dell PowerEdge XR hardware. You may have seen the announcement a couple of weeks ago. We have received the Dell Telecom Certified badge for that integration. We have Intel ACC 100 support through our recent work in the space of DPDK, because that's where the relevant drivers come from. And we also have ARM, or more specifically, ARC64 support for both SLI Micro and K3S working on RKE2. Our next step in the space of hardware enablement is that we want to validate the next generation of Intel CPUs, which is usually known under its codename Sapphire Rapids, or more precisely Sapphire Rapids AEE, as the telco-specific version of that. And this generation of CPUs contains a number of acceleration techniques, which were previously provided at least partially through the ACC 100s. And those technologies are oftentimes subsumed under the codename Intel vRAN Boost. So we want to make sure that those are properly enabled and available to our customers within our stack. We are right now in the process of working with our hardware partners and Intel on making that certification happen. And then another very important thing that Gary briefly touched upon previously is that we are working on a proven integration with Juniper CN2 as a third-party SDN option. We are actually fairly advanced down the road of making it possible technically, and we're basically working on the go-to-market parts of that at the moment. The longer-term roadmap in this area is that we want to make a real-time kernel for SLI Micro available on the ARM platform. The real-time kernel right now is only available on the x86. We are investigating additional hardware offload scenarios by using NVIDIA DPUs of the type BlueField-2 and BlueField-3. The advantage from a customer point of view this will bring is that certain parts of the stack overhead can be completely removed from the x86 silicon, which basically means more capacity available to the workload. And at the end of the day, a smaller hardware footprint will be sufficient to accommodate the same application in those cases. And then another, it's a bit of a detail, but another thing that we're basically waiting on upstream for right now is synchronous Ethernet support in SLE Micro, because we're waiting for the Linux kernel community to land those patches. And as soon as they are available, we will take them and backport them from whatever kernel they land in into the kernel that is currently under use in our operating system versions. Last but not least, observability. You will most likely know that Rancher has a monitoring stack for metrics and logging already, and that is generally available for a very long time. We have a new open source project in the form of the OPNI project, which will provide more centralized full stack observability, and that is going to become available within our next big feature release in the next 6 months. And then at a later point in time, we also want to enable AI ops on top of that, which is also an element of OPNI, which requires probably a little bit longer time than 6 months to mature enough to be called generally available. But that's an interesting addition to traditional observability that we're working on right now. And that is actually all I have in terms of roadmap. And I want to now transition to talking about the concept of validated designs that we've already talked about briefly before. So as Gary said, the key thing to understand and take away about ATIP is that it is not just a bunch of components. The sum is larger than, so ATIP is larger than the sum of its pieces, basically. So we are introducing a concept of validated designs internally as a, let's say, a working method to ensure that the sum of all the components plus all the necessary configuration provides what they need to provide for certain use cases. So validated designs are essentially significantly more opinionated. They prescribe and integrate and pre-integrate configuration that align with use cases that we recognize as relevant and important. And they also adhere to SUSE best practices in terms of stack design and stack operations. Included in a validated design is everything you need to really set up the stack according to whatever requirement you might think of, be it security, configuration, infrastructure blueprint, stack architecture, and of course the software components within the stack. We are going to quality assure, certify those validated designs. We will obviously evolve them over time, and we will regularly and comprehensively test them also in terms of regressions as new components come in, because like with any other end-to-end solution, there are a lot of moving parts under the hood. They get updated all the time, and it is onerous for our customers to keep up with that. We frequently end up in discussions that customers, on the one hand side, want new features, but on the other hand side, don't want to go through the burden of redoing all the validation work. So we are going to take that burden from them and provide it as a validated design that we maintain. And the validation results in the form of which tests are running, which tests are passing, which tests are failing, will be made available in public so that our customers can be assured and know exactly what is being validated within a given validated design. And we will create one or a number of validated designs within the context of Silva, depending on where the market takes us. I want to talk briefly about how we're going to do this. This is a new initiative that we're calling stack validation. So stack validation is the mechanism of regularly testing our validated designs. The mechanism for ATIP specifically is going to be based on the generic mechanism that we're creating for the entire Edge business unit, but it will build on top with telco-specific validation topics. So we will use telco use cases and telco-specific test workloads. We will use telco-grade hardware. We will look at typical telco-grade performance and availability requirements, which will most likely manifest themselves in additional test suites that we will run. And we will, of course, offer the possibility to validate customer-specific setups if that is what our customers are requiring. One last word on solution lifecycle, because that is obviously an often asked question. Right now, for any customer that buys ATIP today, we essentially have a rolling release concept, which basically means all the components follow their respective life cycles. Calling out a few important elements of the stack, SLE Micro has 2 releases per year, and each of them receives 4 years of support. For K3s and RQ2, we're mirroring the upstream Kubernetes lifecycle, which is 12 months plus 2 months security fixes. For Rancher Prime, we have 2 releases per year and an 18 months lifecycle. And as we've talked about the automation and the management stack that makes rolling these changes out into your production environment easy, there's nothing to be afraid of from these frequent updates, because if everything works well and everything is properly validated, a version switch of, for example, the Kubernetes version that you're running should not be more than just changing the version string in your Git repository specification, and then the GitOps engine should detect that change and perform the necessary update functionalities. Of course, it has to be defined according to a customer's requirement how exactly the upgrade mechanism for a Kubernetes cluster should look like, because depending on cluster architecture and the needs of the workload, there are different strategies that need to be implemented. But that is something that we can work out together with our customers. In the future, on the bottom half of the slide, we will, in lockstep with the introduction of the validated design concept, we will create solution level releases based on validated designs, and we will also introduce, or we're planning to introduce, long-term support options. The default will be that for each validated design, there will be 12 months of standard support, largely governed by the Kubernetes lifecycle that I've talked about. Each validated design will use version pinned components and receive maintenance, security updates, and other bug fixes via zstream releases. So if you're familiar with the concepts of semantic versioning, it's the x.y.z part of the version that can, of course, change. We will only pin the major and minor version, and we expect that there will be 2 or 3 releases of a given validated design per year. And this is expected to be also part of the October 2023 release of our stack. I think that is all I have. So thank you very much for your attention. Thanks for watching this. And I wish you a successful rest of your virtual conference experience. Have a look at the other sessions, and otherwise I'll see you soon somewhere, sometime.
Thank you very much, Tim. Thank you very much, everyone, for watching.